nice to have that on the screen at the beginning. So now we'll move on to more subgroups with the general linear group. So first remember that we stated this somewhere earlier. This is the set of all invertible n by n matrices. With elements in R. And we showed explicitly for at least the 2 by 2 case, but it works all the cases. This is a group with matrix multiplication as the operation. Why? Well, what's the identity? Where I, n, is the identity, the identity matrix. Because if I multiply the identity matrix by any matrix, I get the matrix back, right? Because A, I, n is equal to A is equal to I, n, A, right? And A times A inverse. How do I know A inverse exists? I said so, right? I only allowed invertible matrices. And remember, matrix inverses, only square matrices are invertible, so it works on both sides. Even though matrix multiplication is not commutative. And if I multiply two invertible matrices, remember that's the condition for invertibility from linear algebra. Two matrices are invertible. Any matrix is invertible if its determinant is non-zero. And then by a basic theorem of linear algebra, the determinant of the product is the product of the determinants. Well, if I multiply two non-zero numbers together, I don't get zero, right? Those are just numbers. That implies that AB is invertible. And in fact, its inverse is B inverse A inverse. All from reminders from linear algebra. So that's an important group for any fixed dimension n, the general linear group. It turns out this entire sub area of study in abstract algebra called representation theory, because matrices are so nice to work with, we try to represent groups, ugly groups, with a matrix representation, and then I can apply all the power of linear algebra to do it. So let's look at some easy subgroups in our problem section. First one I want to look at is exercise 1H. This is section 2.3. And I want to look at number 1H, which asks us if the following set is a subgroup or not. is that a subgroup or not of the general linear group with of the matrices with integer coefficients? Well, obviously it's a subset, right? Because there's 4 matrices with integer coefficients. I want to test if it's a subgroup. So what are the tests for subgroup? First test for subgroup. Yeah, that's the hard one. What's the easier one? Does this have identity? This is matrix multiplication. Does any of those act like the identity for matrix multiplication?
First one?
Sure, that's a 2 by 2 identity matrix, right? So my identity is good. Now closure. Well, it's a lot of work, right? I know if I multiply by the identity by any of these, I get the same thing back, so I don't have to worry about it, right? I times the second matrix, so all I'm going to worry about is the square of this matrix and this matrix times everybody else. So let's do a couple of these. -1, 0, 0, -1. And then square it. -1, 0, 0, -1. According to the laws of matrix multiplication, what do? It's the dot product of the row with the column, right? So that's 1, and that's it. Right? -1 times -1 plus 0 times 0. Over here, it's -1 times 0 plus 0 times -1. 0 times -1 plus -1 times 0. And finally, 0 times 0 plus -1 times -1. There's the matrix squared is the identity. So that's closed. Let's multiply the second matrix by the third matrix. Okay, by the rules of matrix multiplication, what do we get? -1 times 0 plus 0, well, I get 0 there, right? -1 times -1 is 1. And 0 times 0 is 0. We get -1. And then 0 times, we get that. Is that one of my matrices?
Yeah.
It's the fourth one, right? So I multiply the second one by the third one, I get the fourth one. Let's just do one more. Improve. Show closure. You have to try them all, right? Actually do it. But let's square this matrix. So the third matrix. And if I use the rules of matrix multiplication, what do I get? 0 times 0, we get -1. 0 and 0, 1 and get 0, and then finally -1, which is the second matrix, right? So the square of the third matrix is the second matrix. If you try them all, and you should, this is a lead for homework, finish this problem, 1H, and show that you have closure. But then there's a really nice thing going on here. One of these elements behaves like, this is the clue, one of these matrices behaves like the imaginary number I. It can't be this one. Why? Because I square it, I get 1, right? What happens when I square the I matrix? I get -1. Well, here's a square that gave me something else. See if you can establish that this matrix behaves like I, complex multiplication, and all I'm really doing is powers of I. I squared is -1, I cubed is -I, and I to the 4th is 1. Right? So this is a matrix representation of the group of 4 elements, actually. 1, I, minus 1, and minus I. Okay, so finish that one for homework. I think that's a nice exercise to practice with your matrix multiplication and demonstrate that this really looks like just a closed set of those complex numbers. It's a matrix representation of that group. Okay, number 11 is more classic. Same section, number 11. Let G be the set of all matrices of the form A, B, 0A, such that A and B are real numbers, and A is not 0. I want to show that that's a subgroup of the general linear group 2. So, subgroup, what do I need to show? Closure first, I like, right? So we have 4 things to show to prove this is a subgroup. Closure. How do I show closure? I pick 2 of them and show that 2 different ones, right? So AB, 0A, and then I pick a different matrix that looks like that. How about CD, 0C? If I multiply those 2 by the rules of matrix multiplication, what do I get? What's the first entry? AC, right? And then I have AD plus BC. And then I have 0 times C plus A times 0. And then what's the last entry? 0 times D plus A times C. So I have these 2 entries are equal. That entry 0, and this is a different one. So yes, it's exactly the same form, right? It's AC and AC are the same number here. 0 is where it belongs, and this is my new D, right? So this is an element in that group. We do have closure. All we have to do is get exactly the same form. What else do we need? Identity. Right? If I let, in the original form, A equals 1 and B equals 0, it says A can't be 0, but B can be 0, so indeed I have identity. What else do I need? Identity, closure, and be a subgroup. What else? Inverses. Well, by the way we do matrix inverses of 2 by 2 matrices, what is the inverse of this matrix? Remember how we do it? How do you do the inverse of a 2 by 2? Well, you divide by the determinant, right? What's the determinant of this matrix? What's the determinant? 2 by 2. What is it?
A squared minus B.
0 times b.
Oh.
Yeah, so the determinant is a squared. And then remember what I do to the inside to get the 2 by 2? I swap those 2 elements. And I negate the ones on the other. That's the inverse of that matrix, which of course looks like what? 1 over A, 1 over A, 0, and minus b over a squared. Is that belong in this collection? Sure, because this guy's 0, those two are the same, and that guy's a third value, right? So this is in G, so I have everything I need. It's closed. Is it? Yeah, real numbers. If this was integers, I'd be in trouble, right? Because it's divided. With real numbers as entries, this. So this is a nice little subgroup. Therefore, G is a, never forget to write down the last part, a subgroup of the general linear group of size 2 over the real numbers. Questions? Closure, identity, inverse. That's how I prove subgroups. That's where we're heading. One more nice problem to bring you back to linear algebra, because it's so nice. Let T of x, the transformation of the vector x, be defined as a matrix times x, where A is n by m. Now, what has to be the size of x? Where does x live? Remember how I do matrix times vector? I dot product a row of the matrix with a vector. So how long are the rows in an n by m matrix? M, yeah. So those live in Rm. But when I multiply the matrix A times the vector x, how big is the answer? Well, remember, so if B is equal to AX, one of the most important ways of thinking about matrix multiplication is this forms a linear combination of the columns of the matrix, right? Where the coefficient of the first column is the first entry in X, the coefficient of the second column is the second entry in X. So if I'm forming a linear combination of the columns, how long are the columns? N, right? So T is a transformation, is a function that maps vectors in Rm to vectors in Rn. Now remember that Rn for any size with vector addition is a group. It's one of the first groups we looked at. Because the 0 vector is the identity. Every vector, the negative of the vector, is its additive inverse, and doing addition here, not multiplication. Yes?
Is this going to end up being a subgroup because it's not going to be invertible, right? It's on a square matrix.
Correct. Well, the A is not going to work, but
Okay.
something else will work. Consider the kernel of that map. And what a kernel is, it's the set of all things that get mapped to 0. That's the same as the null space of the matrix, which is equal to the set of all x in the source space in Rm such that Ax equals 0. It's the solution set for Ax equals 0. Kernels will become really important as we go forward. I want to prove that this is a subgroup. That T or null A is a subgroup of Rm. Well, what do we need? Closure. Suppose x1 and x2 are in the kernel. What's my group operation? It's addition, so I need to show that their sum is in the kernel. So what is T of x1 plus x2? Well, it's the matrix A times the vector x1 plus x2. And by the rules of matrix arithmetic, what can I do with A times the sum of two vectors? I can distribute, right? That's AX1 plus AX2 number matrix times vector distributed over vector addition. But x1 and x2 are in the kernel, so what's this result? The zero vector. This is the zero vector plus the zero vector, which is the zero vector. So we have closure. The sum is in the kernel. So we have closure. What else do we need for a subgroup? Identity. What's the identity for vector addition? The zero vector. Is the zero vector in the kernel? If I multiply a matrix times zero vector, I get the zero vector. So I have, by inspection, 0 is an element of the kernel. And what else do I need? Inverses. So if x1 is in the kernel, is negative x1 in the kernel? Because if a times x is 0, then a times negative x, that's really a times negative 1 times x is the same as negative 1 times ax. Remember, I can pull constants out. That's minus 0, which is 0. So I also have inverses. And this is a very important subgroup. In general, we'll get a subgroup structure out of a kernel of a map. Okay, that's it for today.